Alrighty, welcome back. We are at the end of Math 107. We're in Math 107 and we're at Lecture 20. And I don't know if I'm going to label this A or B or not because it depends on how it goes as to where we finish up. But our objective is really to just graph some basic trig functions, A sine bx. We don't have any vertical shifts or we don't have any horizontal shifts. We do have a vertical stretch and compress, and we have a horizontal compress or stretch, horizontal. But I'm sure you guys could shift all around, but that's not an objective of the course. So we're just basically looking at curve sketching in these forms, and the things that we're going to want to look for are called like the amplitude, the period, the zeros of the function, amplitude, period, zeros. And we want to look for some max and mins. And what we're going to do is really concentrate on just sketching one period. But as we go through this, we'll see that these curves just go on and on and on and on forever. But we're just going to sketch for one period. Okay, and there's not a particular one section of the textbook, so I want to point out that we're just going to do some selected parts from 6.5. The unit circle is not an objective of Math 107 because we're right triangle trigonometry folks, but the unit circle is a nice little tool for seeing where we're getting our numbers to when we do our sketching. And so if you're taking this by video, this should be on your Visa link, so that you can get a copy of that, and then everybody in here has a copy. I'm going to talk to you about this a little bit. So we're just going to look at units, the unit circle on 6.5, just because it's going to make our curve sketching of our basic sine, cosine, and tangent functions easier, I hope. Okay, everybody good? All right, so first thing we want to do is talk a little bit about what this thing is that's called a unit circle right here. And at the top it's called the unit circle, and sometimes people might like to call it the 1 unit circle. 1 unit, a circle, unit 1, just means that your radius is 1. So you'll notice that it's touching the point 1, 0, 0, 1, negative 1, 0, and 0, negative 1. If you wanted to draw a 2 unit circle, you would just go out to 2, 0, 0, 2, negative 2, 0, and 0, negative 2. Our trig functions, our values for our trig functions are simply ratios of adjacents over hypotenuses, opposites over hypotenuses. So if we can always make the radius 1, life would be great. If you made the radius 2, it would still reduce down to the same value for the sine and cosine. So one of the nice little things about the unit circle is that when you were looking for, say, 30 degrees, or that's a radian measure of pi over 6. Let's see if I can sort of sketch that in here. 30 degrees, pi over 6. Because the hypotenuse is 1, you know right away for this angle, that's 30 degrees or pi over 6 radians, that the cosine is the adjacent over the hypotenuse. Well, the hypotenuse is 1, so the adjacent, which turns out to be the x value, is the cosine. And if you're at pi over 6 or 30 degrees, the opposite, which is the y value over 1, turns out to be the sine. So down at the bottom of this little unit circle deal, it's written for each ordered pair x and y, x is going to be the cosine of the angle and y is going to be the sine of the angle. And again, that's because your angle will be with respect to the origin here. So if you come along the x-axis, that's an adjacent side, and your hypotenuse is always over 1. I mean your adjacent side over 1. And your sine, wherever you are, happens to be the y value, and that's over 1. So the nice thing about a unit circle is you can just think of an ordered pair x, y, x being the cosine, y being the sine. Just a different thought and approach to this. The other nice little thing about the unit circle is, and we talked about in section 6.4, going beyond the acute angles into the other angles, it's easy for you to see that if you were looking at 150 degrees, which is going to send the terminal side over here, that this little triangle right here is really this little triangle reflected over. So you would see that you still have the same measure of that angle there, so the x would be the negative square root of 3 over 2 and the y value the 1/2. Okay? All right, so this is basically what we did in section 4.6, learning to identify the values of the trig functions for other angles. Everybody okay with 6.4? Is everybody okay with section 6.4? You seem to be when we went through it. All right, so our job today is, well, how do you sketch something like y equals the sine of x? How do we graph y equals sine of x? Okay, well, if we use this little unit circle, we know and remember, we're in the real number system, so along the x-axis we have real numbers, and along the y-axis we have real numbers, because we're in the real rectangular coordinate system, so we don't go put little degrees down here. Okay, but when we go back to our unit circle, we have it expressed in terms of degrees and radians, but radian, as you remember, is the real number measure. So before we turned on the tape here, what we're going to try to do is use the angles that we already know the exact values for and plot them, and then we'll get the picture of the curve. All right, so before the camera came on, I just wrote down pi over 6. I just punched away in my calculator. So pi over 6, which we know is just a real number measure, that's approximately 0.52. So if we have a 30-degree angle, its radian measure, we could call it pi over 6. That's an exact value, or that's about 0.52. And so then I just took the other angles between 0 and 2 pi that had a reference angle of pi over 6. So basically I just said 5 times pi over 6 to get 2.6 and 7 times pi over 6. You have all the same reference angle here. All right, and pi over 4, those were some we were given. And the reason I did this is so I know where on my coordinate system to plot pi over 6 and where to plot 5 pi over 6. Okay, so everybody sees where this comes from? All right, so I'm just going to go to my rectangle, to my curve here. Pi over 6 is about 0.52, so that's about halfway here. Pi over 6. And then pi over 4 is about 7.78. I'm just reading right off the sheet here. So pi over 4 is about 0.78. That would be about halfway to here. I have to write down here a little bit. 0.78. Oops, I meant to write pi over 4. And pi over 3, is about 1.05, so pi over 3 is about right here. Okay, and then we're at pi over 2, which is about 1.57, that's about halfway here. Do you see where these numbers are coming from? And so what I'm trying to do is show where they are on the real number system, the real coordinate system, the x-axis. Okay, then we go to 2 pi over 3, which is, let's see, where are we, 1.57. So 2 pi over 3 is next, and that's about 2.09. So this is like 2 pi over 3 right here. And then 3 pi over 4 is about 2.36. So 3 pi over 4. 5 pi over 6 is about 2.6. 5 pi over 6. All right. Do you get the hang of that? These are just real numbers that are fitting right on our rectangular coordinate system. Okay, so now I'm going to jump and not put in every single thing. I'm going to go from, I never put in pi over 2. Oh yeah, I did. Pi over 2. And then let's go to pi, which is about 3.14. And then let's go to 3 pi over 2, which is about 4.71. That's 3 pi over 2. And then 2 pi is about 6.28. All right. So my key points I'm going to be looking at really are 0, pi over 2, 3 pi over 2, whoops, that's not 3 pi over 2, sorry, 3 pi over 2 right here, and 2 pi. All right, it's looking a little messy, but it was important to me that you saw these are all those radian measure angles stuck along there. Okay? All right, so now we're just going to read off our chart here that because this is a unit circle and the hypotenuse is 1, for y values, for the sine of the angle, all I've got to do is pick up the y values. Okay, so when I'm at 0 radians, starting right here at 0 radians, the y value is 0. Okay, now let's go up to pi over 6. At pi over 6, the y value is a half. Here's my pi over 6. This looks like about a half. Do you see these numbers where they're coming from? Okay, when we go to pi over 4, pi over 4 is square root of 2 divided by 2. That's about 0.7. Okay, so at pi over 4, we're at about 0.7, so that would be somewhere right here. The square root of 2 over 2. 3 pi over 2, I think, is about 0.86. Does anybody know right off? 0.866. Sorry. Approximately 0.866 for square root of 3 over 2. So at pi over 3, we're about 0.86. Okay, and then once we get to pi over 2, the value of the sine is 1. So in my first quadrant, counting off these angles, my curve is going to look like this. Okay? Everybody good so far? All right. Then when we start, continue on, the next one we look at is 2 pi over 3, and the value of the sine at 2 pi over 3 is 0.866. So 2 pi over 3 is right here, and there's the 0.866. The next is 3 pi over 4, and that's a square root of 2 over 2. 3 pi over 4, that's about 0.7. And then did I put 5? Yeah, 5 pi over 6 right here is a half, right there. And then we got to pi. That looks like 3 pi, but that's part of the number there. At pi, the sine is 0. So when I went around in that second quadrant there, I have this part of the curve. Does everybody see where all this is coming from? All right, naturally, we are not going to plot every one of these little points once we start sketching, but you just need to know they didn't fall out of the sky. Okay? Everybody doing all right? Okay, and after pi, I kind of got tired. But you will notice that the y values, that's a negative 1/2. That's about a negative 0.7. This is about a negative 0.866, all the way down to negative 1 when you get to 3 pi over 2. So what's going to happen is 3 pi over 2, you're going to be at negative 1, and the curve is going to come around like this. And then, as you continue on, when you're at 5 pi over 3, you've got like a negative 0.866. 7 pi over 4, you got a negative 0.7. 11 pi over 6, you got negative 1/2. So these y values are getting actually getting bigger because you're going in the positive direction. And then you get back to 0 once you're at 2 pi. So the curve continues around like this. Now, all we've done is 2 pi, but as you know, the curve just keeps going round and around and around for more angles. So the curve continues on like this, and it's just going to go like that forever. And also, recall you can go negative directions, and so your curve is going to come down like this. Okay? All right, let's look at a picture in the book that might look a little bit better than mine. Probably will look a little better than mine. Okay, this is the bottom of page 657. Bottom of page 657. Okay. All right, here's the graph of a sine curve that just goes on and on forever. Notice that we basically graph from 0 to 2 pi. Okay, when you go from 0 to 2 pi, the curve is just going to start repeating itself. So we have a special word we use for the distance the curve goes before it starts to repeat itself. What does somebody call that? Anybody know?
Period.
Period. Okay. The book calls it 1 period or cycle. In the math department here at State, we just call it a period. We go 1 period. It's how far you go before the curve starts to repeat itself. So what is the period of the sine curve? 2 pi. No matter where you are, if you measure off 2 pi units, the curve will start repeating itself. Okay? Is this curve 1 to 1? No, so therefore it really doesn't have an inverse. And do you remember we kept punching the button on the calculator going inverse function? All right, one of the things about an inverse trig function is you have to have a restricted domain on the original function in order to have an inverse. So y equals sine x would never have an inverse unless we did a restriction to make it 1 to 1. And to make it 1 to 1, you'd have to go from negative pi over 2 to pi over 2. So the sine curve has to be redefined between these two angles in order to be able to use your calculator for an inverse sine. Okay, so that's why we stayed with the positive acute angles between 0 and pi over 2. All right, the period is how far it goes before it repeats itself. What's an amplitude?
The height it goes.
Okay, the height that it goes. All right, what is going to be your maximum height for this? 1. What is the maximum value of the sine curve? Maximum value of the function? 1. Remember, value of the function is the y values. All right, what is the minimum value of the sine curve?
-1.
-1, because that's your smallest value. For 1 period, we'll just look at 1 period. What are the zeros of this function y equals sine x for 1 period? Pi, 2 pi, and
-0.
0. 0, pi, and 2 pi.
So you don't count the what's over here?
Well, if you were just doing the 1 period,
Oh.
but yeah, if you were doing them all negative pi, every multiple of pi. A lot of times you just say k pi, where k is an integer, negative 2, -1, 0, 1, 2, 3 kind of deal. So in general, it's every pi units. There you'd have a 0. Okay, everybody good? All right, so now let's play around with this a little bit. Suppose I write y equals 3 sine x. Y equals 3 sine x. With all your expertise on transformation, what does this do? A vertical stretch. All your old y values are multiplied by 3. So your old y value here is 0. So 0 times 3 is 0. At pi over 2, the old y value is 1. So the new y value would be 3. So you'd be way up here. So it's going to stretch it up here. And once you're back to pi, the y value is 0. So it's just going to come back down like this. And then, of course, I'm off the bottom of the page here for going down. Let's see if I can put this sheet underneath. If you were at 3 pi over 2, the old y value was -1, so now it's going to be down here at -3. Send it way down like this. Whoops, that looked bad. And then back up to 2 pi. So this would give you a vertical stretch. Okay, is that pretty easy? All right. Let's draw a clean cut sine curve again, and let's do a horizontal stretch or compress. All right, so we want to graph y equals sine x for 1 period. Okay, now to clean this up, we want 1 period. To clean this up, we're not going to put in every real number. We're going to put in the zeros, max, and mins. So we'll put in 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so all I've done is I'm lifting the red curve up, but just kind of removing some of the things that look a bit confusing here. And we'll put 1 and -1, and the sine curve looks like this. Okay, all right. Now we want to look at graphing y equals sine 2x. Okay? All right, so the argument here is now 2x. The 2 is multiplied times the x. So that's going to do with the horizontal. Is that going to be a horizontal stretch or compressing?
It's different when you're dealing with the x.
Right, when you're working with the domain, this is where it always seemed backwards. Remember that? It's always seemed backwards on that. So this is going to be a compressing by a factor of a half. The old x values are going to be multiplied by a half. All right, so let's look at the old x values. The x value here is 0, so now it's 0. Okay, the old x value here, where the y is 1, is pi over 2. So we'll multiply pi over 2 times a half, and so now we have pi over 4. Now we're going to go back and double check these, just so you believe it. All right, so this is going to go here. All right, this old x value is pi, so we'll multiply it by a factor of a half. So now we're at pi over 2. So this one comes over to here. And this old x value is 3 pi over 2, so we'll multiply it by a half. So now we're at 3 pi over 4. 3 pi over 4 will be right here. Everybody with me? 3 pi over 2 times a half. And now 2 pi times a half puts me at pi. So a compressing, we've taken this and we've squished it towards the y-axis. All right, but we are, we're never happy without checking. So let's just check it. If I put in pi over 4, I'll be looking at the sine of 2 times pi over 4, which is the sine of pi over 2, which is equal to 1. If I put in pi over 2, the sine of 2 times pi over 2 is sine of pi, which is equal to 0. Okay, is everybody a believer? Is everybody? Yes.
How did you get the sine of 2 times the pi over 4 is equal to the sine of pi over 2?
2 times pi over 4 is 2 pi over 4. 2/4 reduces to 1/2.
Oh, okay.
I'm just reducing it as I go. Okay. Sure?
Mm-hmm.
Okay. All right. So what is the period for y equals sine 2x? What's the period? Pi, because that's how far this curve goes before it starts to repeat itself. So the period here is pi. Okay? All right. Now, sometimes it's bad when you've been teaching as long as me, so I have another way of doing this. So you can do this any way you want to. If you want to do your compressing, that will be fine. If you want to look at another way that I do this generally, I'll show you, and then it's your choice. All right, and here's the way I normally do it. We want to sketch one period of y equals sine 2x. Okay, now the reason I'm showing you this is because if I were going to graph sine 2x, I probably would not want to first go graph y equals sine x and then do all the compressing. And I know that the sine curve is going to always start down here at 0, 0 if there's no vertical shifts, okay, or horizontal shifts, okay. We're not doing those in this course anyway, so we know we're going to start at 0, 0, and I know the shape of the curve. I know the shape of the curve. So another way to do this is to say, okay, this angle right here needs to be between 0 and 2 pi, because I hadn't seen this in any books. I'm just telling y'all, this is just a nice and easy, compact way of doing it. I want to find all the values of x such that when I substitute into 2x, it's going to give me the angle between 0 and 2 pi, which is the normal period for my sine curve. So we'll just stick 2x right in the middle and solve for x by multiplying through by a half or dividing by 2. And that tells me that when I pick a value of x between 0 and pi, it's going to give me the full sine curve. That it's going to start at 0, that it's going to end at pi, and then you can just divide this up into fourths because a sine curve is always going to start at 0. It's going to reach its max 1/4 of the way in, back down to 0, minimum 3/4 of the way in, and then back in. So if I divide this pi up, this is going to be pi over 4, pi over 2, 3 pi over 4, just fourths in here. And then we know the amplitude is 1, so we just go like this. Whoops, something like that. And we got the graph of the curve pretty quickly. The period is 2 pi. The amplitude is 1. The maximum value of this function is what? 1, and the minimum is -1. The zeros are for this curve 0, pi over 2, and pi. Yes?
Wouldn't the period just be pi?
Yes, it would be. I don't know where that 2 came from. Thank you for correcting me. Yes, thank you. The period for this one is pi. The period for the normal curve is 2 pi. Thank you, thank you, thank you. Yes, the period is how far it goes before it repeats itself. And again, I need to say this because it ends up that students seem to forget that this curve just continues to go like both directions forever and ever, but we're just concentrating on one period. Everybody good? All right, let's do one more of these and then we'll work on cosine. Is this easy? Answer that's yes. You may want to make up the problem. Hurry up. Nobody wanted to make it up. Okay. All right. Do y'all like my way of doing this? I think my way's easiest. What's the amplitude?
4.
4. You just get it from right here. Amplitude 4. All right. To find the period, if you're going to do it my way, the normal sine curve goes from 0 to 2 pi. And we say this one ain't normal. Okay? So we're really looking for all the values of x that I can substitute into x over 5 that will give me those values between 0 and 2 pi. So what do I need to multiply through here by to get x in the middle? 5. So we get 0 less than or equal to x less than or equal to 10 pi. So what's my period?
10 pi.
Okay, we say our period is 10 pi because it's a distance of 10 pi. Anywhere along the curve you mark off, the curve will start to repeat there. All right, so we're only sketching one period. Period is equal to 10 pi. All right, so we'll mark off 10 pi. And what's the middle one going to be? Remember, you're dividing it up into a half, and then what's half of that? 5 pi over 4. Half of 10 pi.
Yeah, I was wondering about
Half of 10 pi, woo, is 10 pi over 2.
which is
Half of that is 10 pi over 4. Right, I know that's 5 pi.
Yeah, I'm confused.
You're confused?
Yeah, keep passing it up.
Well, let's start again then. If I confused you, everybody else must be confused.
I think it's easier just to say 5 pi over
10 pi. Half of 10 pi is 5 pi. Half of 5 pi is
2.
5 pi over 2. So what's halfway between 5 pi and 10 pi?
10 pi over 3.
How do you find a midpoint? Just add and divide by 2?
Yes.
So if you add 5 pi plus 10 pi, that's 15 pi, and just divide it by 2. Just finding the midpoint, 15 pi over 2. You could look at this as 5 pi over 2, 10 pi over 2, 15 pi over 2, 20 pi over 2 if you wanted common denominators and see it. Okay, our amplitude is 4. And then our sine curve just always starts down. These are always nice and easy to draw. Oops. And there we have y equals 4 sine x over 5. Notice that if I check and I put 5 pi in for x, sine of 5 pi over 5 is just pi, and the sine of pi is 0. And if you put a 15 pi over 2 in for x, this thing is going to reduce to 3 pi over 2, which is where you have your minimum. How are we on y equals sine x? Good? Questions, anybody? Anybody need another practice? Good? All right, let's look at cosine curves then. Okay, y equals cosine x. And let's go back to the unit circle. Wherever I put that sheet, start with a new one. Okay, this time we're going to be graphing the cosine, and because we're on the unit circle, we can just look at the x values. Because our hypotenuse is 1, so the adjacent is always an x value. All right, so when we start at 0, the cosine is going to be 1. If we went around the circle, pi over 6 at 30 degrees, the cosine is square root of 3 over 2, which is about that 0.86. The cosine of pi over 4, square root of 2 over 2, which is about 0.7. Pi over 3, the cosine's a half, and then at pi over 2, the cosine is 0. All right, so let's get that sketched in. Actually, this time, unless you beg, we're just going to hit the key points. Anybody need to see pi over 6, pi over 4, pi over 3, and all that stuff put in there? All y'all saying, no, I don't need to see it. All right. So when we start at 0, the cosine is 1. And what happens is the value of the cosine, which are the x values are getting closer to 0. So by the time you get to pi over 2, you're at 0. So we'll go 1, and at pi over 2, and if you plotted all those points, it would look like this. Okay? And then notice after pi over 2, the x values are negative, headed down to -1 once you get to pi. Okay, so pi, right here, it starts to come around like this, because at pi, the cosine is -1. And then notice the x values start getting closer to 0 again. By the time you get to 3 pi over 2, you're back to 0. It comes around like this. And then once you pass 3 pi over 2, the x values get closer and closer to 1 again. By the time we get back to 2 pi, and it looks like that. Okay? And so all I did was go around one time. So the cosine of 0 is 1. The cosine of pi over 2 is 0. Cosine of pi, -1. 3 pi over 2 and 2 pi. So for the normal y equals cosine x, the amplitude is 1. The period is 2 pi. Okay? And it always starts up, and your zeros are at pi over 2 and 3 pi over 2. Okay? Everybody good? All right, so let's put it all together and sketch something. All right, let's sketch y equals 1/2 cosine 8x. Okay, let's graph y equals 1/2 cosine 8x. What's my amplitude? Just read it right here. 1/2. So along the y-axis, we're going to plot 1/2 and -1/2. Okay, if we're going to look for the period my way, or we can think of this as being a horizontal compression by a factor of 1/8. we can say the normal cosine period goes from 0 to 2 pi. We want all the values of x that if I substitute into 8x will give me those special numbers between 0 and 2 pi. So we're going to multiply through by 1/8 or divide by 8. Okay, so what is my period? What would your answer on the test be when it says, what's the period? You would say 2 pi over 8 or pi over 4 if you reduce it. Pi over 4. All right. So we're asked to just graph one period. Oh, excuse me. One period. We'll mark off pi over 4. And then we're just going to mark off these key values. And I always just jump to the middle. What's half of pi over 4? Pi over 4, and you just multiply by half. Pi over 8. And what's halfway between 0 and pi over 8? Pi over 16. You're just saying pi over 8 times a half to get pi over 16. All right, so usually what I do, I go 1 pi over 16, 2 pi over 16. So what's the next one going to be? 3 pi over 16. Because that one's 4 pi over 16. If I used a common denominator 16s, it's easy to count it across. Everybody good? All right, so you're graphing a cosine curve, so you're going to start up here because the cosine of 0 radians is 1. 1 times a half is a half. And if we put pi over 16 in here, 8 times pi over 16 is pi over 2. And the cosine of pi over 2 is 0. You put a pi over 8 in for x, the cosine of pi is -1. -1 times a half is -1/2. So the curve's going to go like this. 3 pi over 16 in here will reduce to 2 pi over 3. And then pi over 4 will reduce to 2 pi. And there's one period. Okay? Everybody good? Normally on a test, I would say identify these key points. I mean, these are very important key points because you see your zeros, you see where your max occurs, mins. Yes, so go ahead and get your brain set on putting those in. All right, everybody good? Questions? All right. Do we need more with sine and cosine? Anybody need another example? Everybody's all right. All right, let's graph y equals tangent x. Let's graph y equals tangent x. And we're actually just going to do one period here. One period for y equals tangent x. Okay. And we'll be able to read these right off the chart. Let me get a new chart here. See if I can find one. If I know sine and cosine, how do I know what the tangent is? Tangent in terms of sines and cosine is sine over cosine. So at 0, the tangent is 0 over 1 or 0, sine over cosine. So at 0 radians, the tangent is 0. Okay, let's put a pi over 4 in here because that's going to be easy. Pi over 4. What's the tangent of pi over 4? Sine over cosine? What is it? Tangent of pi over 4 is 1. So we'll find 1 on here. Okay, let's go to pi over 2. Pi over 2. The tangent of pi over 2 would be 1 over 0, and what does that tell you? That it does not exist. All right, let's just play on the calculator a second. All right, I'm going to make sure I'm in degree mode because that's usually the easiest thing to see. We're in degree mode. All right, so I'm going to look at 89.9999 degrees and get the tangent of it. That's getting pretty close to 90 degrees. And in fact, I could write the limit as the tangent as t, I'll just call it t, approaches pi over 2, but just a little bit smaller than 90 degrees of tangent t. Let's see where this is going. All right, remember limits? Getting ready for your exam. All right, we'll do the tangent, clear, quit. Okay, the tangent of 89.999999 degrees. Okay, and that gives us 572957795.13. Put in some commas here. Looks like it's 572,957,795. Okay, I could put in the tangent of 89 point and do a few more nines. And that E13 just means you're going to start at 5.7, take that decimal and move it 13 places to the right to make it bigger. So where would you say this tangent's headed? In what direction? In the direction of positive infinity. All right, so we're going to have a vertical asymptote at pi over 2. X equal to pi over 2 is an asymptote. And you know that in the first quadrant, all the sines over cosines, which are tangents, are positive. And it's getting close, you know, it goes to 1 and it just keeps getting bigger and bigger. So the curve will look like this as it approaches that vertical asymptote. All right. Now, tradition has it that so you don't have a break in your graph with this, that you go the other direction now instead of continuing on past pi over 2. So we're going to go in the direction of a negative angle. All right, so this time we're going to go this way. Again, at 0, we're already at 0. This way would be negative pi over 4, and what would be the tangent of negative pi over 4? Sine over cosine. What's the tangent of negative pi over 4? Negative 1. So here is negative pi over 4. Here is negative 1. Okay, we get down here at negative 90 degrees. The tangent of negative 90 degrees, or negative pi over 2, is sine over cosine. All right, well, again, that's undefined. But if you're in this quadrant, aren't all your tangents negative? So if you put in the tangent of negative 89.999999 degrees, where do you think this thing is going to approach? Negative infinity. Okay? Negative infinity. So, as we approach negative pi over 2, but just a little bit smaller than that, the curve is going to, go like this. And tradition has it that if you have to sketch one period, you would sketch it between negative pi over 2 and pi over 2 so that you get a nice curve. After this, your curve is just going to, if you're going to sketch more than one period, your curve is going to go like this and continue on. And over here, it's going to go like this. Okay, so it just continues on and on. So, my questions then are, what's the amplitude of the tangent curve? What's the amplitude? Okay, I hear 1. Would you say 1 is the maximum height?
Negative infinity to infinity.
Amplitude, there is none. Because the curve goes both directions forever and ever and ever, it heads off to infinity. What is the length of the period? What's the length of the period before this curve starts to repeat itself? Is the period pi over 2? Does the curve repeat itself from 0 to pi over 2?
It's pi.
Okay, from negative pi over 2 to pi over 2? That's one complete curve, right? So the period then is, when you're wanting a distance, you take big number minus little number. So pi over 2 minus the negative pi over 2, which is 2 pi over 2, which is pi. So the tangent curve only has period pi units. Every pi units, even if this is going to be pi right here. If you went from 0 to pi, the curve will start to repeat itself. The sine and the cosine have 2 periods, 2 pi for its periods, but the tangent only has pi units. Okay, only has pi units. All right, so how do you normally graph just one period of a tangent curve? You identify the asymptotes. The tangent curve is going to go through 0, 0 with no horizontal shifts, and we don't do, they're called phase shifts in trig. We're not going to do any phase shifts, which you guys could do, and it just looks like this. All right, let's try another example. Let's look at y equals 7 tangent of x over 6. Okay? How's that 7 going to affect my graph? How's that 7 going to affect it? It's going to be a vertical stretch, and the place that it affects it is really right here. When you get to pi over 4, it's now going to be a 7, so it's just going to go up a lot faster and fall a lot quicker. But it's still going to have that same shape. And when we're sketching one period without the tangent curve being there, you're not going to visually see a big difference there. All right, so we're going to sketch y equals tangent of x over 6, 7 times x over 6. The curve is basically going to look like this without any effort. Of course, that's not going to be good enough because we're going to want some asymptotes. This, by the way, is curving up. It's not hitting that asymptote. All right, how do you think we're going to find the equation very easily for these asymptotes? Would you consider going with my quick and easy method? The normal tangent curve has asymptotes at negative pi over 2 and pi over 2. And let's just stick that x over 6 in between, because we want to know all values of x, that when we put in x over 6, it's going to give me that tangent curve there. All right, so let's multiply through by 6, and we get negative 6 pi over 2 is less than x less than 6 pi over 2. I'm off the page, thank you. And so negative 6 pi over 2 is negative 3 pi is less than x less than 3 pi. All right, so what's my equation for this vertical asymptote here? X equals 3 pi. What's the equation for this vertical asymptote? X equals negative 3 pi. What is the period for this curve? What's the period?
6 pi.
Okay, all you have to do is like subtract to find distances. 3 pi minus a negative 3 pi is 6 pi. Okay, period 6 pi. What are the zeros of this function? 0. The only place it touches there is 0. Let me ask you a couple other questions. What is the limit as x approaches 3 pi, but a little bit smaller, of 7 tangent x over 6? What's the limit as x approaches 3 pi, but just a little bit smaller? You would say infinity. The y value heads in the direction of infinity. What is the limit as x approaches negative 3 pi, but just a little bit bigger, of 7 tangent x over 6? Remember, this is a little bit bigger than negative 3 pi because it's moving in the more positive direction. So what's the limit here? Where's the y value headed? Negative infinity. Negative infinity. Okay, everybody good? All right, one more, and then I'm going to have to claim you're experts unless you ask me something. I want you to state the periods for each of these functions. Y equals 7 sine 2x over 3, and y equals 25 tangent 5x over 7. All right, state the period for me. Find it. Find the period. How far the curve would go before it started repeating itself. Yeah, you're basically getting x in the middle of your inequality by itself. Was that your question? But don't forget to get the distance between those values. Okay, let's go for sine. 2x over 3 has to be between what numbers? 0 and 2 pi, because the normal sine curve goes between 0 and 2 pi. What do you need to multiply through by to get x in the middle by itself? 3 halves, right? Every little term is multiplied by 3 halves. So 0 is less than or equal to x, less than or equal to 3 pi. So what is my period?
3 pi.
Period is 3 pi. What's my amplitude?
7.
7. Let's do a quick sketch. We'll mark off 7, negative 7. Divide this up into fourths. What's the middle one going to be?
3 pi over 2.
Half of 3 pi is 3 pi over 2. What's halfway between 0 and 3 pi over 2?
3 pi over 4.
3 pi over 4. All right, this is where if you'll get common denominators, things are easy. 3 pi over 4, 6 pi over 4. So the next one is
8 pi
3, 6,
over
9. 9 pi over 4, because that's the same thing as 12 pi over 4. All right, does the sine curve start at 0 or up here at 7?
0.
0. It starts at 0. And we just hit our max, mins, and zeros, and there we have it. One period. One period. Good? Questions? If it had been cosine, it would have started up at 7 and then hit your key points, which you're going to not forget to label. Okay? All right. Tangent curve. What's the amplitude?
It has none.
Tangent curve, doesn't it go off to infinity and down to negative infinity? It doesn't have an amplitude, so there is none. Don't get tricked on your test. All right, we know the tangent curve always has this nice little shape for one period. I have an asymptote here, here, and the curve's going to look like this. Now, the effect that the 25 has is that halfway between 0 and this asymptote, this y value here would be 25. Halfway between 0 and here, whatever that is, the y value is negative 25. Okay? All right, how do we find the asymptotes?
Inequality.
The inequalities. What do you put on each side here?
5/2 and negative 5/2.
Okay, don't usually say or equal to. We just say between negative pi over 2 and pi over 2 because the function is actually undefined at pi over 2. All right, so what do I multiply through by?
7 pi over 5.
Yeah. 7 pi over 5. Oops, no pi's. 7/5
Yeah, 7
and
fifths.
7/5. All right, so that looks like that's going to be negative 7 pi over 10 is less than x less than 7 pi over 10. So what is my period?
14 pi over 10.
7 pi over 10 minus a negative 7 pi over 10 is 14 pi over 10, which we know reduces to 7 pi over 5. So that is the length you could mark off, and the curve would be repeating itself. So this vertical asymptote is x equals 7 pi over 10, and this one is x equals negative 7 pi over 10. Okay, everybody good? Can you do it? All right, let's flip through the book. I think we're in good shape. We only did the unit circle in here just to help us see where these numbers were coming from. At the bottom, page 657 is the graph of your sine curve, one period. And your book does other transformations we're not required to do. All you have to do is what I told you to do, a sine bx. Bottom of page 659 is the graph of your cosine curve. Okay, and then they did other transformations. If you look at the exercises, you want to be careful that you just pick problems to do. There are no webassigns for this because this is basically just curve sketching. You want to be real careful, though, if you go to page 669, that you do the forms that we did in class, which would be like 21 and 22 and 29, 30. And you could do some of the matching at the bottom. You just want to be careful that, you know, we're meeting the objective of the Math 107 class. Okay, and then in 6.7, this was the graph of your tangent curve, one period. And notice at the bottom of page 673, does that look like something I sort of pointed out to you, your limits? You want to get good at limits just so when you're in your calculus class, you got a good understanding. And we've done that all along the semester. Okay, then they did transformations. This also has other functions in it to graph, but we're only interested in this course for tangent. So if you're on page 678 looking for some exercises, the ones that you probably would want to play with are number 27. And that looked like what we did in class. Just graph one period, identify your asymptotes. 28 looks good. You see the others in here? I don't really see any others that totally meet the objectives of this course. They're pretty easy to make up, and you can double check them on your calculator or plug in some points. Are you experts at curve sketching? Okay. This ends Math 107. Yay! You're finally the expert. Tomorrow, I'm going to take questions from 6.4. That's your trig functions beyond 90 degrees, pi over 2, that we work with, and questions about this, and then we're going to talk through as a general review of your exam. And you want to be sure that if there's something that you need drill and practice with, go back to that videotape, or go back in here, go back to your notes, or you go look to the library and look at the videotape. Because for a review for the final, we can't sit here and work tons of problems. We've done that already. So I will just be turning the pages and prompting you and reminding you. Okay? Everybody good? Questions? Comments? Okay, that's it.